Well, welcome back, guys, and as ever during this time with the schools being closed, I do hope you and your family are keeping well. So what we're going to look at now is the electric field strength between parallel plates. So if you remember, we've done capacitors, so I think you'll have a good understanding of what happens in parallel plate systems. So what I want to do now is I want to show you how we would work out the electric field between parallel plates in a capacitor. So I'm going to start by drawing a capacitor, or more importantly, just some parallel plates. Now you might ask, why am I doing parallel plates? Because we'll do point charges later on, because the field shape is a little bit more complex. So there's our parallel plates. We'll pull electrons off this plate and leave it positively charged, and we'll drive those electrons onto this plate, and that makes it negatively charged. And you now know, of course, there's an electric field in here from plus to minus, and within the plates that field is uniform. So I'm being careful to try and draw these field lines the same distance apart and to put their direction on. Okay, now I know we've got the fringing field out here, but we're not going to be looking at that today. So what I'm going to do is I'm going to put a positive charge in here and see what happens to it. Okay, so don't be confused by the fact that I put the positive charge here. Okay, that positive charge is still inside the uniform field and will feel a force. So there it is, positive charge. We'll give it charge Q, and you know that it will feel a force this way, and we'll label that force F, okay, the force acting on that positive charge. So what I want to do is I want to take the ideas that we've got here to work out what is the electric field strength in this gap. So we know that the electric field strength is the force per unit charge, but is there another way we can derive that and a more useful formula that we can get? So let's see if we can derive a formula for the electric field strength in here. Now you might say to me, well, FJ, it's pretty obvious because we know the electric field strength in the gap will be equal to the force on the charge, the force per unit charge. And I'll say to you, yeah, that's all very well, but how would you work out the value of that force? How would you know how much charge is on the object? Okay. And what's really interesting is the electric field strength in this gap is still the same strength if you get rid of that charge, as long as it's a small charge. In other words, this object does not create this uniform field, it's just in it. Okay, so if we could get rid of that point charge, the electric field's still there, and what size would it have? So follow me through on this. We know the electric field strength in here will be the force felt by this test charge, F over Q, and the force that that charge will feel, yeah, if we rearrange this, is EQ. Okay. Now, this is where you just kind of pull ideas out of the sky. I'd like to remind you of work done. Okay. You might remember that the formula for work done, so I'm going to use the symbol W here, is force times distance. Okay. I won't go into the details of the force must be and all that sort of business, which direction this is. Okay. But we know that work done is force times distance. And we also know that work done, now I hope you remember this, is voltage, potential difference, times charge. Okay. Now let me just remind you why that is. Work done is in joules. Voltage is the number of joules per coulomb, and this is in coulombs, so joules per coulomb times coulombs is joules. So work in electrical circuits is VQ, or QV we normally write it that way around. Okay, so the work done will be force times distance. Okay, now you might be struggling to see why have I done this. Okay, that if we have to take this positive charge and push it that way, we will do work on it, okay, equal to the force that we put on it multiplied by the distance that we moved that force through. And when we let it go, it'll come back, yeah, and it'll give us that energy back. It'll give us that energy back as kinetic, okay, and that kinetic energy will be equal to the work that we did, or QV, VQ, okay. So, what's the force on this object? Well, if we rearrange this, yeah, the force acting on this little thing will be VQ, there's the D, upon D. Now, you'll notice to begin with here that we're beginning to get some things that we can measure. The force is going to be difficult to measure, the charge is going to be difficult to measure, but the voltage across here is going to be easy to measure, and the distance between those two plates is going to be easy to measure as well. Now let me just show you a little trick that you won't have noticed. What happens if you don't measure the voltage across here, but you measure it across half the width? A bit like a potential divider. Okay, if there's 1,000 volts across this, there'll be 500 volts halfway across it. But if you've got half the voltage over half the distance, V over D remains the same, which is really quite interesting. So what we're going to do now is we're going to use this that we've derived here to work out a formula for the electric field strength in this gap, in the parallel plate capacitor, or between the parallel plates, using numbers that we can easily, or quantities we can easily measure in the laboratory. So let's bring things together now. So we know the force on a charged particle in this electric field will be equal to EQ. Okay. But we also know the force on the charged particle will be VQ upon D. So we can say VQ upon D, that's the force, is equal to EQ. Okay. Now, I hope you can see where this is going, and it's so clever. The Q's go, so Q divided by Q goes. I don't like to use the word cancel. I'm quite aggressive about this. They don't cancel, okay? They divide one by the other, so you lose the unit, but Q over Q becomes the number 1. So it isn't lost from the system, it's a multiplier of 1, so we can forget it, okay? And if you do that, E equals, oh my word, E, the electric field strength, anywhere in this system, because it's a parallel plate capacitor, it's a uniform field, it's a special case. In the uniform field, the electric field strength at any point will be V over D. Okay. Now I hinted at that earlier on, that if I go halfway across, the voltage across the gap will be halved, the distance will be halved, so V over D stays the same. The electric field everywhere in there, okay, as long as you're inside the plates and not in the fringing field, will stay the same. And isn't that clever? What it means is that if we set up a parallel plate system, not point charges, it's more complex, a parallel plate system, okay, the only thing we need to work out the electric field strength in there, E, okay, yep, the force per unit charge, is a voltmeter and a ruler. Incredibly clever, isn't it? Okay. Finally, what we'll do is we'll just quickly look at how the units here work out. Okay. And I think you're familiar with this already. So the units of E well, you know that E is defined as the force per unit charge, so it will be in newtons per coulomb. Okay. And what's really interesting is if you start to pull the dimensions out of these, okay, quite tricky to do. You could try that if you want. Newtons comes from F equals ma, okay, and coulombs will probably come from amps, because an amp is a coulomb flowing per second, okay. Those units must be the same as those units. So a newton per coulomb, yeah, is exactly the same as a volt per meter. Now, if you hadn't seen that before, volts per meter sounds radically different to newtons per coulomb, but in fact, they're exactly the same unit. So this bit's quite easy. Let's do a quick example of calculating the electric field strength in a parallel plate capacitor. So here we go. I'm going to make the numbers really easy. Here's my parallel plate capacitor. It's one plate. There's the other one. Should have them the same size really. And the connections. And remember that we put the charges on these plates, or we separate the charges by connecting it to a high voltage power supply. So let's connect the left hand plate to 5,000 volts. Watch out for that in exams. Yeah, 5 kilovolts. And let's make this plate grounded. So this is the 0 volt plate, 0 potential. Okay. So this one is going to be very positive if it's at 5,000 volts. And this one is going to be, well, you could say 0, but of course the electrons have come off that one onto this one. So it's easier to understand if you don't ground it. Okay, what we're really saying is between here and here is 5,000 volts. I'll give you an example. This could be at 15,000 volts, but this would have to be at 20,000 volts. So there's a potential difference of 5,000 volts across them. That's the best way to think about it. Okay, let's separate them by a certain separation, a certain distance. Okay, now you notice with these things, with parallel plates, it's a distance measured with a ruler. So we use D, and we'll make D here equal to 1 meter, okay, to make life easy. So let's calculate the electric field strength within that parallel plate system. It will not be outside it where the fringing field is, only the uniform field inside. So we know the electric field strength is volts per meter, V over D. Okay, I know this is easy. We know that. Okay, remember, it doesn't matter what the voltages are on the plates, doesn't matter what they are. What is the potential difference? Okay, so the potential difference here is 5,000 volts. So 5,000, yeah, watch out for K, 5 kilovolts. And watch out for, with me particularly, with my questions, millimetres and centimetres here. Okay, 1 metre, so that's easy. So the electric field strength here is 5,000 volts per metre. Okay. Now, remember that the electric field strength is also the force per unit charge. So don't forget, if you get a question on this, that the electric field strength is 5,000 newtons per coulomb. Okay, because they might then chuck a charge in here and you'll think, oh, hang on, well, how does that work? Okay, well, you can work out that V over D will be equal to the same number, and the force on the charge will be this number, okay, because you'll probably know the charge, so you can work out what force that charge feels, and then you can work out what acceleration it has. So very quickly, let's do another quick example, and I think fairly soon you'll pick this up quicker than I'm drawing. So here we go. What I'm going to do is I'm going to take these plates and I'm going to narrow them down. So I'm going to put them closer together. Okay. What's really interesting is the size of the plates does not matter. Okay. It doesn't matter what size the plates are. So this is not about capacitance. It's just the fact that you get a uniform field in the gap and you're connecting them to a power supply. Okay. I won't worry about what the value of charge is on these plates. I will just say that this one's positive, okay, and this one's negative. I'm not saying that the charge here is the same value as the charge there. That's not what I'm saying. I'm just saying there is positive charge there. Okay. We'll separate them by 0.5 meter. Okay. And again, this would be 50 centimetres, so D here equals 0.5 metres. We'll put a voltage on them, so we'll put 2.5 kilovolts here, 2,500 volts, and we'll make that 0 volts, or at least there's a potential difference across them of 2,500 volts. And I think, again, like I said, I think you're probably ahead of me here. The electric field strength in this one, E is V over D. You'll notice that E is, well, half the voltage. Oh, do you remember what I said? Here, okay, I could imagine what the voltage was at this point, 2,500. Or I could set it up completely differently, disconnect it, earth it, and then connect it to a 2,500 volt power supply with a separation of 0.5 meters. So 2,500 divided by 0.5. In this case, that's a special case, yeah, we get exactly the same value of electric field strength. 5,000 volts per meter, or if you prefer, newtons per coulomb of charge that you put in that gap. Good. So, I hope you have a good understanding now of not only what the formula is for electric field strength in a parallel plate capacitance system, but also you can use the formula to do calculations. So I do hope you found that video useful, a little short one, and it was on the electric field strength in parallel plate capacitors. Can you now chase off and watch one of my FJ's physics videos? I'll put a link at the top to it, on electric fields. Okay, what I do there is I set up a parallel plate capacitor, I put a charged object between them, and you can actually see the effect of the electric field in the parallel plates on the individual charged particle. It's quite interesting because I then start messing around with the separation of the plates. Think about what would happen if I did that. And I start messing around with the voltage across them. So, I hope you enjoyed that video. I'll be making another one taking this topic a little bit further, and I look forward to seeing you then.